It seems to be a bit of a pattern when typically session 2 seems to go straight on from session 1. So, okay, so Q0 is the start state of N. Point 2, point 3. Now, big N's, the bigger machine that has two parts, N1, N2. What's its capital F? In other words, what are its set of detect and accept states? Well, just this seems fairly obvious. It's just simply the union of the accept states of N1 union with the accept states of N2. Because what are you trying to do? Because if if the last input symbol comes in, you read your string, your input string, and if you're in a state where N1 would accept, so if one of your states here is say belongs to F1, well that's okay. Then F, your machine N would accept because N1 has accepted. Okay, and similar logic for F2. So if one of your elements of F belongs to F2 and the last input symbols come in, then your left, your state here is now belonging to F2. So F2 has detected, has accepted the string. So if F2 has accepted the string, then F has accepted the string. That's how we set it up. Okay? So that seems fairly obvious. Right? It's just so the set of accept states of your big machine N, in other words F, that set, well it'll just be the union of these two. So, right? Okay, now here's where the devil pops up. The hardest, in my view, the hardest part in constructing these machines is typically the transition function, the delta. Okay, so what's your delta for the big N, this machine that should detect, should recognize the union of languages A1 and A2. Alright, so it's like a 4-part. Now I'm still a bit hazy, and I'm not sure whether it's me. Is it something I'm missing, or is it something missing in the text? Is it Sipser? I'm not sure. Maybe a bit of both. I don't know. But I'm still feeling a bit fuzzy. Not clear. It hasn't really clicked, not crystallized on the use of these eta arrows. So you see what I mean. Now, maybe you've figured it out already, and that's great. So hats off to you. But I'm still puzzled. All right. So the transition function for N. Now, if your current state Q. Now remember, what is a transition function? It's just some function that tells you what the next state will be. Effectively, that's all it is. Now, it's an NFA, so that next state may actually be a set of next states. Right? And each member of that set corresponds to a machine that an NFA, a machine that processes independently the others. Right? So in an NFA, this transition function gives you the next state, or a set of next states. Okay, so say your current state belongs to Q1. Well, then just use the transition function D1 to find the next state, right? Because maybe you're looking, the input string maybe contains a string that is a member of language A1, right? So you want to keep looking for next symbol in that string that belongs to A1. So that would do that for you. Now, if this current state, if it's in a string that the string is part of language A2, in other words, your current state belongs to Q2, then you'd want to use the transition function for machine N2, because you're looking at the string that you hope belongs to A2, the language A2. Right? So these two make a certain amount of sense. Now, here comes the devil, as I said. These two. Right? Let's see. I wonder if I can figure it out in real time. Okay, so you can't see the previous session. Okay, so let's see. So the current state is Q0. That's the starting state of your big machine N, right? And remember, from that starting state there were two eta arrows. One going to starting state of N1, and the other eta arrow going to the starting state of N2. Okay. This I think I understand. I don't think that's too hard. So you're in the starting state, and you've got two eta arrows going, right? So you pick up the states that the eta arrows point to, and they will be what? Well, Q1 and Q2, right? Because that's the starting state of N1, and that's the starting state of N2, and both these states get pointed to by eta arrows from Q0, and Q0 is the starting state of big N. Okay, so that I followed, right? So you're in the starting state of N, and you follow the two eta arrows, and you pick up these two. So that'll be your next state, or the set of next states. Okay. And A is eta. So you look at, in other words, you look at the label on those arrows, and they're eta. So that makes sense. So I follow that. Okay. Now this is the one that still puzzles me. And well, let's do a bit of thinking in real time. Maybe you can figure it out. Maybe you have already figured it out, or maybe you're also just stuck. I'm really hoping that once I've done a whole bunch of the problems, the exercises at the end of the chapter, there's 65 of them, that I hope this use of the eta arrow will clarify. Because you remember a couple of sessions back, I put like a triple exclamation mark comment on some remark that he made, and I wrote it out verbatim, that whether you follow the eta arrows before you read the next input symbol, or whether you read the input symbol first and then you follow the eta arrows. Yeah, I don't think that was talked about prior to that. So still a bit fuzzy on the use of eta arrows. Okay, so what's going on here? Okay, so in the current state is in the start state of N, okay, and the symbol on the arrows from the start state is not eta. Well, I don't understand that, because when you look at the diagram of the previous session, there are two arrows coming out of the start state of N, right? And both of them are labelled eta. So how can this even be? I don't understand this at all. So is Sipser implying, in a sense, somehow that these etas get used once and then they become something else? I don't understand. It seems to, like, if that didn't exist, then I guess now my understanding of eta arrow is, so you're in some state and you're trying to calculate the next state, and let's say it's state k, and then coming out of state k are eta arrows. Well then your next state, when you calculate it, would be k, but because of the eta arrow, you also include in the set of next states is the state that the eta arrow points to. So say you're, so now you've got like two, you've got a set now of two states, and so you will copy the machine, and now you have two machines moving down in a sense in parallel, independent of each other. Now, if you just have this, then so you will have a machine at Q0 and at Q1 and Q2. At the next state. The next state will be the set of Q0, Q1, Q2. Right? Okay, so the next character gets read, and there's still there's a Q0 in the next state. So it again does this. So that's my understanding. And so at each input, as each input comes in, does that make sense? You're just going through this infinite loop until you come to the end of this input stream. Does that make sense? No, I'm confused. Well, I guess if I were Sipser, I'd be able to clear it all up for you, but I can't. That's one of the disadvantages of my approach, of what I'm doing. Alright, so if I do, maybe I'll come back to this in the problem solving session once things become clearer. But I'm being honest, I'm puzzled. This particular aspect I don't understand. If some of you do, please email me. Okay. Now next theorem. Now these three theorems showing closure, proving closure for union, concatenation, and star. They have a lot in common. They'll incorporate an NFA, one or two of them, inside a bigger NFA, N, okay, and then they'll connect up in a different way, in different ways for the three cases. But that incorporation of one or two smaller NFAs inside a bigger N NFA, that's in common. Okay, so you'll notice that. All right, now let's go back to when we're trying to prove closure of the operator concatenation, and we got stuck. But now we'll take a non-deterministic computation type approach, and we'll solve it fairly easily, as you'll see.